This is section 6.2, the law of sines. In this section and the next one, we are going to be solving oblique triangles. We talked about right triangles in the previous section, but the majority of triangles don't have a right angle. And so we can solve those triangles using trig, we just need a different approach. So from geometry, we know that two triangles that meet the following conditions are congruent, meaning that they have exactly the same angles and exactly the same sides. And these go in order. So ASA, we have two angles and the included side. So we need to have the information for two angles and the side that's between them. AAS, two angles and a not included side. So two angles and then a side that's not between the two angles. SAS, two sides and the included angle, so two sides and the angle between them. And then SSS, all three sides. Okay, so if we have this information on two triangles, we can show that they are congruent. We don't have side-side angle. It doesn't guarantee a unique triangle, but we do know that there are at most two triangles with the given information, whatever we have, okay? And then if we have all three angles and then no information on any of the sides, that only guarantees that the triangles are similar, meaning proportional. It does not say that they are congruent. They could be congruent, but that's not enough information to say that, okay? Now, when it comes to labeling oblique triangles, we label them essentially the same way we did on the right triangles. The only difference is with the right triangle, our C was always the right angle. On an oblique triangle, we don't have a right angle, but capital letters for your angles, and then opposite your angle, you have the lowercase side. So angle A, side A, angle C, side C, and so on. Okay, so when it comes to solving oblique triangles, we have four cases. There's the case one where we know two angles and a side, where we have either angle, angle, side, or angle, side, angle. Okay, so that's case one. Case two is where we have two sides and an angle opposite one of the given sides. Okay, SSA, that's what we're talking about here, where we don't have necessarily a unique triangle. Okay, case two, we're going to be coming back to this. We call this the ambiguous case. We're going to come back to that. Then we have case three, where we have an SAS, and case four, where we have SSS. We are going to be able to solve cases 1 and 2 using the law of sines in this section. Cases 3 and 4 we will tackle in 6.3 using the law of cosines. Okay? So what does the law of sines say? It's fairly simple. So if we have a triangle with angles A, B, and C, with sides of length A, B, and C labeled the way we just talked about, sine of A over A is the same thing as sine of B over side B, is the same thing as sine of C over side C. Okay? So to show that this is true, I'm going to consider two cases. Okay? Here, this triangle has only acute angles, and on this one we do have one obtuse angle. So we're just going to show that this is true for both of them. Okay? So what we've done is we have this main triangle with acute angles, and they've dropped this down here, which is the height of the triangle, and we did that to make two right triangles. Now what I'm going to do is I'm going to find a way of talking about H. Now the first thing I'm going to consider is the triangle made up from C, D, and A. So that's this left-hand right triangle. Okay? Well, what do I know about that? Well, I have this angle here. I don't have all of C because that's split. D is a right angle. B is not even in the triangle I'm interested in, but A, I do know something about A, and I can write a trig value that has an h in it. Sine of angle A is opposite over hypotenuse, so h over b. And that means that my height is equal to b times sine of A. Okay? Now I'm going to come over to the other triangle. So this is triangle CDB. CDB. We're going to do something very similar here. If I'm talking about angle B, I can find sine of angle B, and it is opposite over hypotenuse, which is h over A. Therefore, h is equal to A sine of B. Okay? We're going to come back to those two in just a second. Come look at case 2. Okay? This had an oblique angle in it, and the way they drop in altitude to find the height is you just extend that line going out and drop it down, and that's your h. And this side right here is your c, only from angle A to angle B. Now, if this, whatever this angle is, this is 180 minus that, because it makes a 100-degree angle down at the bottom. This angle and this angle are supplementary. Now first, let's look at the triangle that is CDA. CDA. Okay, so what do we know? Sine of A is opposite over hypotenuse. So h over b. And that means our h is equal to b sine of A. Okay. Now let's look at this little tiny triangle. Okay. So we're going to look at the triangle that is CDB. Okay. Now I'm going to talk about sine of 180 degrees minus b. And this would be equal to opposite over hypotenuse, so that equals h over A. Now, you can use the difference rule for sine if you want to prove it, but if you recall when we were solving equations involving sine, we got one answer for our angle, and then to get a second potential answer, we did 180 minus that angle. And that means that this is exactly the same as sine of B, h over A. So our h is equal to A sine of B. Okay? Now, if you look at these two cases, each of these, by splitting it up into two right triangles, we were able to find two values for h. And what's more, in both cases, we got the same two equations for h. So if we take both of these together, we can solve both cases together from here on. We set this h equal to this h. So I have b sine of A is equal to A sine of B. And then it's nothing, just divide this side by A, that side, well, both sides by A, both sides by B, and you end up with sine of A over A equals sine of B over B. Okay, now we've only proven this with A's and B's, but if you just drop an altitude from a different angle on each of these, from each angle, you will get the whole piece of all of this law of sines, okay? So just by changing that where the altitude is and following the same process, you will get all of this. And what's more is that if you flip every single fraction here, you have the same relationship. This version is most useful when you need to find an angle. And this version is most useful when you need to find a side. But either version will work in either case.